Uh, Good afternoon, good morning, wherever you are, good evening, depending on where you are. This is webinar number 23 in our series, in our center's webinar series, which we started in response to us all being apart from each other in the pandemic, and it has turned out to be a nice forum to reach out and have a discussion with a wider audience. So the speakers today are myself, Saunak and Gregory Farage. We are both in the Division of Biostatistics in the Department of Preventive Medicine at the University of Tennessee Health Science Center. I'm Professor and Chief of Biostatistics, and Gregory is a postdoc in working with us. So today we will give you a brief introduction into Julia, which we think is a fast, friendly, and powerful language for data science, and we hope to impress you of the same. So here's a rough outline of what we will counter. I will tell you about our history with Julia, which began with a chance encounter, and then outline why our group's work has, why we decided to pick Julia for our work. After that, Gregory is going to tell you about the design and language syntax of Julia, some key features, benchmark, package ecosystem, language binding, how to call other languages. And then we'll give you a few examples. The first example would be kind of vanilla flavored, like data analysis, the kind of thing that you might do in a consulting project if you're a statistician. Then I'll give you a short example of optimization, the kinds of things that we do a lot in our research. And then Gregory is going to give you a simple example of how you can fit neural net in Julia there, and we'll end with a summary, and we'll be available for questions from you after that. So why Julia? So our journey towards Julia began with a chance encounter with Ken Lang, who was a seminar speaker in 2015. I was the seminar organizer, and I got to spend some time with him. Ken Lang, for those of you who don't know, is a really decorated statistician, statistical geneticist, and mentor of many outstanding quantitative scientists. And I was telling him about what we were doing, and he said, "Hey, why don't you look at this new language called Julia?" And I was a little bit surprised at that point because but on the other hand, coming from a person of his stature, it was definitely worth a look. And he showed me like a page of code of what he was writing for a future book of coding a GLM, generalized linear model, iteratively reweighted least squares. I looked at the code, and immediately I could understand what it was, how it worked. And just the looks of it told me, maybe this is worth a shot. And I will show you something similar a little later to kind of convey the same feeling. We started using Julia that summer. It was version 0.3. The language had been announced 3 years before in 2012. And since then, the language has grown a lot. Even our group, we have published about seven packages so far that are using Julia. And I have to say that it would probably not have been possible given the resources that we have, had it not been that we are using Julia. So what are our reasons for picking Julia. So our group is working on statistical genetics and data and statistical methods for large omics data. So that's the kind of use case. And for a lot of things that we do, we have to do numerical optimization. We have to manipulate and compute on large data sets. Kind of that's the kind of work that we do. The number one reason why we picked Julia was that it was familiar and very easy to read. Having known some other programming languages like R or MATLAB, it was immediately kind of very clear how to learn this language. And so it was familiar and it was very easy. It was very straightforward. I knew what to do. The second thing was it's open source. I think that that's maybe one reason why I would have picked Julia over MATLAB, even though syntax-wise they are kind of similar. The third reason was fast and easy linear algebra. You will see from an example why I'm saying this. Our work involves a lot of linear algebra, and just the way the language design works and computation is easy and fast. And the good thing is that the prototypes can be as fast as what you might write in C or C++. So there's no need to write your algorithm, then, oh, it's not running fast enough, let's write it in C and then call it from C. That is not necessary. The next reason was that it is the way the language is designed. You can program in many cases almost the same way that you might write an algorithm on a piece of paper or pseudocode. Your actual code doesn't look very different from that. And again, I'll give you some examples of what that looks like. And finally, there are there's being a modern programming language, parallelization, shared memory, distributed computing, all these concepts are built into the language design from the get-go rather than being added on later. So you have a lot of control. Not only can you do distributed or parallel computing, you also have a significant amount of control on how you do it. And finally, little things like interactive notebooks. What I'm giving this talk on so-called Pluto notebook, which is an interactive notebook mixing Markdown and Julia. So let's give you a flavor of what the language looks like, and you'll see what I mean, or what I just said. So consider the problem of least squares estimation. Everybody's familiar, y equals to x beta plus epsilon. And it's well known that you can estimate the regression coefficients beta, the predicted values, the estimated residual sum of squares, and the variance covariance matrix. These are 4 very straightforward equations, right? And this is how you might want to implement that function in Julia. So you define a function, keyword ls, and you give it 2 arguments. You tell that these arguments are matrices, floating double precision matrices. The first line is calculating the size of the design matrix. The next 4 lines look almost exactly like these equations. Notice I can just write I can write beta. I can use Unicode characters. I can write x transpose x. If I was doing it in R, probably the syntax would look similar, but instead of x star b, it would be x % star % b, which is much harder to read than this. So it's just a lot easier. And that's it. So this is an example of how straightforward it is. And this will run almost as fast as what you would you would do if you were coding it in C, C++. So so you can see how easy it is to write, and the piece of code that Ken Lang showed me was something similar. It was not least squares. It was something slightly more complicated, but the syntax was as easy to figure out. So here's a little bit more to show you some sort of land. Is there a difference between the two matrix inverses? I will answer that question later. Yeah, a good question. Yes. So here is another example, a different way of writing a function. Previously, I used the keyword function, but you can also write one-liners like this: fx equals to sin x. Okay, just like you would write on paper. Gx is equals to x squared. So I have two functions, f and g. Now I can plot the function, f of g. I can do it in two ways. I can say plot, x goes to the composition of f and g of x. So notice this is something would be familiar to applied mathematician, composition of two functions. And this is another function. This is an example of an anonymous function. Plot it from -2 pi to pi, and don't give any label to the lines. That's it. This is your. I could write the same thing alternatively in this manner. I can take a function that takes x to, it pipes it to g first and then to f. So this is an alternative syntax using a pipe notation. And you can again see how clean the syntax is, how easy it is to read. 2 pi is a lot easier to read than 2 star pi. I don't have to create a vector of values. I can just plot the function straight itself. So here is another example of that statisticians will appreciate. So one of the things that Julia excels at is abstractions. And in the Julia language designers, those who designed the stats pieces did a great job in creating a very organized system using the type interface in Julia. So the idea is this: all distributions are probability distributions. We know we can do certain things like calculate expectations, calculate the support of the distributions, and or compose, do a convolution of two distributions. All those things, all those abstractions are built into Julia. So for example, in Julia, the normal distribution is a type that is a special case of type univariate distributions that are continuous. So all operations that can be done on univariate distributions can also be done for the normal distributions. So I'll give you an example. Here, I'm calculating the mean of the standard normal without any arguments. This gives you just the standard normal. So this gives you the mean of the standard normal and the mean of the exponential distributions. So it's just mean. If I want to get the lower limit of the support, I can just say minimum. So the function minimum is defined as the lower limit of the support of a distribution. So in one case, it is -infinity for normal, and it's 0 for exponential. Similarly, if I want to generate random numbers, there's a unified interface. If I want to get a matrix, 2x2 matrix of random exponentials, standard exponentials, I just say rand exponential. That's it. If I want to get normal, I will just change this to normal, and that's it. So I don't have to use different functions for every different distributions. So that's one of the things. So all of these things shine when you build even more complicated things like Bayesian inference is very seamless because all these abstractions are easy to implement in Julia. Yeah, you know, for example, Bayesian inference is very simple. You have, if you can specify all the conditional distributions, you can get the joint distribution and then you sample. That's, in concept, that's all there is to Bayesian inference. And that idea can be implemented using these abstractions in Julia. And last, I will just show you, before I pass it on to Gregory, I'll just show you how you could do kind of simple interactive visualizations. As I said, I'm using Pluto notebook to give this presentation, and I can do, you know, this is a visualization of a power calculation. And I can, you know, the more the alternative distribution mean shifts, the power will change. Just give it a minute. Okay, here, you know, etc. So this is just a quick overview, and over to you, Gregory.
Did you want to field Gabriel's question now or later at the very end?
I think I'll do it later. Yeah, but it's a good question. It only takes 5 minutes. Yeah. Gregory?
Yes, all right. Okay. So good afternoon, everyone. So I'll share my screen. Okay. All right. Can you see the screen?
Yes.
All right. Okay. So I will go over like some of the key feature of Julia. I will talk about the syntax. Then after we will see like some benchmark plots to see like the speed compared to other languages. I will talk about the package ecosystem and this package manager. And at the end, I will show you like some example of language binding. All right. So in 2019, there was an article that was published in Nature that was titled "Julia, come for the syntax and stay for the speed." So like Saunak mentioned earlier, what of the appealing characteristic of Julia, it's like it has a very familiar and intuitive syntax. And of course, what we are interested to, it is like how fast this high level language can go. So Julia is still like a scripted language like Python, MATLAB, or R, but it's much faster than those kind of language. So we will see now some example of what are the different comparisons between the syntax with those of those languages. So here I just want to show quickly that is a web page on Julia, official Julia website, where they have like this very nice page where for each language like MATLAB, R, Python, or C++, or Lisp, where they show like what are the main and noteworthy differences between those other language. Meaning like if you are proficient in one of these language, and you can just go in this page and see what are the main differences. It gives you like a very good overview and a nice way like to directly dive in the programming of Julia without necessarily like struggling and how to to see like how you do stuff differently. So here there is like different cheat sheet comparing like the syntax between Python and R or MATLAB. So I did my own. So here, for example, one of the things that you want to know is like how you will add a library or a package in your environment and how you are going to load it. So in Julia, you use like the package manager, and you just like, so this is like the module, the package, and dot plus the function to add the data frame, which is like a package in Julia. So it is very similar to R, like with the install dot packages tidyverse. So it's a little bit different in of course in Python. Then after, like, to load it, the same thing. You can use actually there is two ways to load your package in Julia. You can say using data frames, or you can also use like import. There is also import data frame like in Python, and that's how you load your packages. For the control structures, as you can see, it is also very familiar. So when you coming from one of those language, it is very easy like to go and try to find out like how you will you do your control structure, like the if else or the loop. So the only difference, like here in Python, you have to be very careful about the tabs character when you want to create your function or your loop. In Julia, you just like start with your for, your keyword for or if, and you just need like to end the loop with the keyword end. So like the closing open bracket and closing bracket in R. So now for creating matrix and to have access to some elements, also it is very kind of similar. One of the difference maybe that it's not, it's to note, it's like in Python, in Julia, the indexing start by 1 and it's not 0. So the index of the first element of vector will be 1, like in R. You have the zeros function. And another difference that you have, like, for example, if I want to create like my an identity matrix, so I will use like one of those function in R and Python, but in Julia, you just write the I, like you will do it like in a pseudocode. And the I, if you notice, I didn't put like any dimension, because basically it's an abstraction level of the concept, what is the identity matrix. So meaning like you take like a matrix, you multiply by I, and Julia will infer like exactly what to do with the I matrix, with the linear algebra packages. So to have access to the different element of the matrix, again, like it's very similar. So I didn't put MATLAB, but it's also very similar to MATLAB. So it's very, the learning curve, it's very smooth to code with Julia when you know one of those packages. For creating the function, again, you have like use function, you close it with the keyword end, but also you can write directly like a math notation for your function, like also like Saunak show you some example earlier. So this is also very convenient. Then after to call your function, here it is similar. The way you the order of your argument in R and Python, here you can have like this freedom to inverse it. You can do that too in Julia if you name your argument before, like I did here, for example. And also you can pass like like open for pass like different open arguments or keyword arguments, similarly like you would do with Python or R. So a little note about the function in Julia. So the function in Julia, we use like multi-dispatch. So meaning that what we call a function in Julia, for example, here I create a function f. So the function, it is the name itself, f. But inside the function, the methods, or the algorithm or the code, the command line inside the function, it is called a method. So we can have like one function and different methods. So when you call a function, it will send a dispatch and it will try to match what is the methods that corresponding to the function that you call according to the argument that you have. So usually what happened, you have different multi-dispatch in different language, but usually it's based only on the first argument. But Julia, actually, you have this freedom and flexibility that it will find the methods according to the different keyword argument and the type of which argument. So now I'm going to talk about the Julia speed. So this is like a benchmark that was created, I think, like for the version of Julia 1.1 or 1.0. So it's like maybe like 2 years old. But what you can see that they benchmark different programs. So each of the code, it's like has a specific task, like for matrix multiplication, read and write, like the IO streaming of the data, or recursion loops and so on. So they benchmark all these codes, and as you can see that the Julia basically is more like in the range of the lower level language, like C. So Rust still remains like a little bit more, maybe faster than Julia, but it is like more or less comparable. Like if you compare like with MATLAB, Mathematica, Python, or R, there is a huge difference. So this was a little bit old, and those benchmarks, they are on the Julia website. So you can ask yourself, like, is it like a very objective benchmark or not? How those different code were programmed, were they optimized or not in those different language or not? So I found this website. It is called the Computer Language Benchmarks. And on this website, basically, they have different programs, but the same way, they tackle like a very similar problem. Maybe some of you will be they recognize like the FASTA algorithm, like for sequencing, or the N-body. It's a program used in astronomy. So, and what they have done, it's open source, so anyone can try like to propose new version of the program with the language, but with any kind of optimization. So for the same program, you have different version. And here I put like the fastest one that they are up to date. And still you can see that Julia, it is very close to C. C is still faster. But compare like to Python or even Java or Lisp, is still faster. So here I just like put the median speed of all this benchmark for those different programming code. And as you can see, like Julia, it is fast, not as fast as C for some of this, but it's very close. So now I will talk about the Julia package. So I will say one of the main drawbacks of
Gregory,
Yes.
just a quick question from Shusheng. How does it handle garbage collection? Or
For,
manage memory, was Xu Sheng's question.
how does it? Okay, so the garbage collection, it is. I mean, like I don't know about like the efficiency of garbage collection compared like to other, but it works like more the principle. It's like in Java or in Python. But if you go actually in those, if in this website, basically they have like different timing for the benchmark. They have like the timing for the algorithm and for the code itself, and you have also some timing like how long it takes, like when you start, like with all your computer, including the system and the heaviness of like putting everything together to get this. And I didn't put it here, but you will have like similar results. So for the Julia packages, well, like I was saying, that the Julia packages, the ecosystem is maybe one of the drawbacks in the sense that is a more recent programming language compared to R or Python. Today, there is a little bit over than 6,500 registered packages. And to give you like an idea, like in R, I think there is almost like maybe 16 or 18,000 of packages registered. So you can see like it is like almost like 3 times bigger in other, like in R. I don't know exactly how much in Python, but that is like, I would say maybe, but it's comprehensible too, that one of the lagging in the Julia programming. But the package ecosystem actually is very user-friendly, and I like it a lot. It's very nice. I will give you like an example. So this is a website, juliahub.com, where you can have access to all those packages. So let's say that, for example, you go there and you want to say like, okay, I want to apply a package that do like, let's say that the ADMM algorithm for proximal algorithm, and you will see like what are those packages that can help me, or they have like functional, or they are related to the ADMM function. So, or also you can go find here some topics. I can, for example, I can do like, let's say what they have about like QTL. So that's our 2 of our packages that we develop and we registered, and so on. So this is it is a very good package environment. Then after also Julia comes with a built-in package manager that I already talked about, the PKG. And I will give you like a small example of how it works. So let's say that I'm going here in the REPL, I will launch Julia, and to have access to this interactive package manager, I will press on the closing square bracket, and now I am in the package manager. So now if I go status, all right, so this will give me all the name of my libraries, and that are the references, the version. Here they have the version number, but here's like the UUID of those packages. So here you can add, let's say that if I want to add a package, I will say add the name of the package, and I will, for example, iterate tools. I mean, it will add it. I have already, if it is already there, it will try to update. You can use update, but also it has another good function, which is generate, like is to generate a project. Basically, is to generate an environment, like similarly like what you would do like in Python. You say like generate, okay, and I will say generate like hello. So what will happen, it will create like a folder with those file, which is like the project TOML. You have a manifest, and those file, basically they are a log that will record all the packages that you will use in your project, meaning that now, if I want to go there and I want to activate my project, so activate, like this, no, activate dot. So now if I am in my project, and if I want to try to test like what are my list of packages that I have none. Okay, so now if I want to add packages that I will use for my project, my analysis, or to create a new package, I will add the name of the package, and it will create key entries in the log environment. And like this, it will help like for the reproducibility of your analysis or your package, because the next time you want to load your environment or you want to use like some of those packages, it will check for those versions. Okay, I will go back to the presentation. All right. Here, so these are the packages that's worth like mentioning. So you have like stats-based distribution that we talk about, the GLM, which is very similar to the GLM packages in R. You have Turing for Bayesian inference. For data tools, like you have the equivalent of tidyverse with data frames or queryverse. You have also a bio package for the framework for computational biology. For machine learning, you have access also TensorFlow or PyTorch. They are like wrapper basically of those packages. You have Flux, which is like all written in Julia. And I will make a small demo later on. And also you have language binding with, for example, PyCall or RCall. So like I mentioned before, one of the drawbacks, it is like you don't have a lot of those packages that they are very useful for you. And to bridge this gap, okay, we have those packages that allow you in a very user-friendly way to use your package, or even like to include some piece of code in Python or in R, and you can communicate in those two languages, even like transfer some objects, as I will show you in like in a few moments. And like this, yeah, with the full Julia ecosystem is not fully mature, but you can still use Julia for all the other features that are interesting, and still do not like give up on your favorite or very useful library that exists in other languages. So let me show you an example of how it works. So let's say that I will demonstrate with the simple function, the sum function. So I create in Julia, so this is all in Julia. I will create a vector of random number. I will get my sum. And here, if I want to use the built-in function, let's say in Python, the function sum, I will call my library PyCall, and I will specify, okay, I want to create a function, PySum, and I will say like, use the sum in the built-in function in Python, Py built-in sum, and that's it. I have my this object. Basically, it is when I process like the PySum A, it will process it with Python. So and here we have exactly the same results. So another way to do it, it is like, let's say that you want to have your own function or a customized function. So for example, here, in my directory, I have a small Python script where I have my function to do the sum. And here I will import this script, okay? And in the same way, I will use it to get the results. Another way to do it is like to directly from Julia write the code in Python using the pi and the triple quotation. You write your Python code, then after you just say that, okay, this is, you declare that it exists in Python, and now you say, okay, the sum pi, it will be my Python function that I created earlier. And again, the same, you will use it seamlessly. So you can also import libraries with like, for example, math, or you can use also like take advantages of like some more advanced and more optimized libraries that exist in your language. For NumPy, you will import it and you will use it in the same way. So you have exactly more or less the same thing with R. You could use R call, like here I get it, I got the sum. In the same way, you can also write a small R code. I call my library in R, I get my data in R, and then after I process it and I get like my violin plot. And here you see I will display and I will get like my violin plot in Julia. So, or what you can do also, it's like you here, I will read the data from Julia, and then I will use this summary function in R, this built-in function on my data frame in Julia, and I will get the results from R. So these packages make it very easy, like to cross over, like if you want to try Julia, but you're not sure because you have like those missing packages in the Julia ecosystem. You have the same for Java, you have the C code for C and C++, so it's a very nice language binding packages that you have in Julia. So I will give back the screen to Saunak. Okay. Saunak?
One quick question for you there from Spencer.
Yes.
Is there a performance hit moving data back and forth, or is it in shared memory?
So there was a question like that before. So in Julia, so that it's a longer topic, but in Julia, all arrays are by default passed by reference. So if I say, I'll give an example later. So that reduces a lot of memory requirements, but that's a good question. So I'll now give a quick view of what your workflow would might look like, and there were some questions about the IDE in the chat. I'm here going very basic. This is a command line window here, and I'm gonna invoke Julia right here. It's just like you would do R if you were doing R. And so here is I import a linear algebra library, and let's say I define a matrix A, 1, 2, 3, 4, and I'm gonna just calculate an inverse, something very simple. So notice it took 0.37 seconds. It gives you, next time I run it, it takes a lot less. The reason is a just-in-time compiler. The first time you run a function, it will compile it. The second time you run it, it will run the pre-compiled version. So this is one of the ways in which Julia speeds up the computation. Even though the code is interpreted, using a just-in-time compiler makes things faster. So I'll show the pass by reference here. If I say B equals to A, okay, I have a matrix B, it's also 1, 2, 3, 4. Now if I change A, so A of 1 is equals to 10, okay? Now A is different, okay? But B is also changed, okay? So this is something that you need to know. You know, there are positives and negatives about it. But if you are using large data sets, this means that you are not making unnecessary copies of the data. Sometimes you do want B to be a copy of A, and in that case, you would write B equals to copy of A. And in that case, if I change A back to 1, you know, A is now 1, 2, 3, 4. B is going to be still the same. So you can get the pass by value behavior, but by default, it's a pass by reference, something that, you know, it shares with Fortran and is very useful for large data sets. So this is one. Now let me show you, go back to kind of the
Can I add something just quickly? So one of the interest of this also is, like, imagine that you have a huge amount of data and you're going to use a function. And this function, it is like you will have like to do some processing and it will return like your matrix change. But like if you don't have this kind of pointer of with B, so it will copy all temporary value in your buffer, like of the matrix, make a copy. So it will take time, it takes more memory, and process it and give you back, and you recopy. So in Julia, you have this thing that you can do those kind of processing faster if it is needed. So, okay, back to you.
There are some, okay. So here is a kind of analysis of like a consulting project type of project, you know, type of thing, something, you know, basic that all of you might want to do. This is a data set of fitness measured in a bunch of Arabidopsis recombinant inbred lines that were measured in 2 sites, Sweden and Italy, in 3 years, 2009 to 11. And there's a gene of interest who's called FLC, flowering time locus, which is important for plant fitness, has 2 states, 1 or 2. So this is what, this is how you would import the data. You can see I give you the URL, I just read, and then I give you the first 10 lines, very straightforward. If you want to make a histogram, again, make a histogram. Notice I have to convert it to floating point. The reason is that missing values are a special type, and if a data set has a missing value, I need to convert the data into a double precision number before I plot it. This is a scatter plot. Same deal, very straightforward, nothing very unusual. This is what linear regression would look like if I wanted to do linear regression of fitness in Italy in 2011 on 2009 and FLC. This looks exactly like, almost exactly like what you would do in R, except that there is this formula macro that you have to put in front of the formula. The model formula. Now I will do something slightly more fancy, something dplyr-like, without using dplyr-like packages, just using base functionality in Julia to illustrate the power of abstractions. So let's say I want to do linear regression of all 3 Swedish fitness values. So I create a vector of strings which has the variable names SW09 to SW11. I can do that by just composing the string SW with the vector of strings 0, 9 to 11, and that's very straightforward. Then I convert them into models using this this line here. I convert the strings to symbols or variable names and then to terms, and that gives me these formula terms. So these are basically the formulas that the three formulas, but it's just a one-liner. I'm using the equivalent of a apply function like many times. Now, if I want to do fit all of those models, what I do is I take the list of model, this vector of models, I pipe it to this anonymous function, which is saying take a model M, then apply the linear regression to it on the data agrin, which is the name of the data set, and then pipe to a function that gives just the coefficients. And that is what? This. So you can see, and you know, I could change it to something else. I could just say, you know, if I wanted to see the whole thing, I would, you know, this is the entire table. If I could do it slightly differently using broadcasting, but you know, it's basically the same syntax. Sorry, same functionality, but done slightly differently. Now let me show you an optimization example. This is a bread and butter of what we do, and one of the reasons why we use Julia. So I'll give you an example of gradient descent. You know, the basic idea of gradient descent is if you have a function, you compute the gradient at the iteration that you are and move in the direction of the downward gradient. So I'll take the example of something that looks like a squared loss plus L1 penalty. So just that looks like.
I think we don't see the notebook.
You don't.
Maybe you are on the, you shared the wrong screen or the.
Sorry.
Yeah. Okay.
Yeah. So this is a function f of x that looks like a squared error loss plus a L1 penalty. And I define the function x squared, x minus 2 squared plus twice the absolute value of x. This is what it looks like. If I want to calculate the derivative, I just say derivative f. That gives me a function which is the derivative of that using, and then I can just plot it. So this looks exactly like expected. And this is my gradient descent function. So it has a few nice things. You know, first of all, I can write I have this Unicode delta f. So I have to give the gradient descent function two functions: the actual objective function f, the derivative, the gradient function, the initial value, step size, and a tolerance for reaching convergence. And the algorithm goes like this. I initialize the change variable, initialize the starting value, and while the change is bigger than the tolerance for convergence, the new iteration is the old iteration minus step size times the gradient. And I update the change, update the iteration value, and when it converges, I return it. So if I notice the string here in the triple quotes, this serves as my documentation. So I can, if I say question gradient descent, it will give me the what I wrote here in like rendered in Markdown. And you know, here is the example of how it might work. I say gradient descent f, derivative of f. Notice the abstractions. I'm not actually numerically calculating. I'm giving a function. I'm giving the derivative straight as another function, okay? Not something that is numerically calculated, and give it the initial value, the tolerance, and the step size, and it tells me where it is minimized, which is at 1, and the value of the function is 3 at that point. So I think over to you, Gregory.
Okay. Okay, so we are running over time, so I will try to be brief. So this is an example of the deep learning with the package Flux. So here I call my libraries. I generated like 2 classes of data here, two clusters for the outer cluster, class A, our inner cluster, class B. And basically what we will try to do, we will create a neural network model, we will train it, and we will apply on the testing data set. So for building the neural network, I will use, here I use the function neural network, so it will return me the architecture of my neural network. And I'm just, the function chain is just like to combine my different layers together. And here, like for example, my I will create my first layer. I have 2 inputs, 5 outputs, and the second one, I have to also specify which activation function that I will use. And basically, that is here the neural network that I created. So now that I have my architectures with my activation function, I need to train the model. So for that, I still need like to define what is the loss function and what kind of optimization I will use. So for the optimization, I will use a gradient descent. So here I create a model. So the M is a neural network model based on what I have specified earlier. And here it is my loss function. I can change, use different kind of loss function. So now I have everything like to train. So this piece of code is just like to compose my data in batches with some shuffling if I need it, like for the training. So the X and Y for the input output. I just specify which parameters that I want to train. So I can omit some of the parameters, which sometimes can be useful if you work on transfer learning, for example. So I have my parameters that I want to train. I specify the number of epochs, and just that's it. Here, that is the simplest way to do it. I would just call the function train. You see, like the function with the exclamation point mark, which means that I will use the data set, the optimization and loss, but at every iteration, when it calls the function, my parameter will change every time. So this is the results. So there is another way to do it where more manually you can go deeper in the detail and change, add different thing and customize even more your training if you really want to. So I will go like on the testing. So here I just created my test data set. that is the result, and as expected. So the probability to be like in class A, they are very strong when you are further like from the borderline between the two clusters. And as you can see, like when you get closer to the cluster, it reached like to the 0.5, where it is like more difficult to identify from which cluster it belongs. And here just like a small confusion matrix. All right, so I will stop sharing, and we can, I think we are ready maybe to conclude.
So our closing remarks. So why might you want to consider Julia? I hope we have convinced you that there is a low barrier to entry, that the common tasks that you would do would be familiar if you're using another language like R, Python, MATLAB already. You can use high-level abstractions, mathematical, conceptual. I give you a couple of examples, like the example of distributions, the example of the identity matrix in linear algebra. These can be very powerful. The Julia's Bayesian computation package is extremely good, has performance that is comparable, very good. I wouldn't say better than Stan, but in the same ballpark, even though it is not as mature as what Stan is. The prototyping speed is comparable to interpreted languages like R, Python, MATLAB, and speed is comparable to C. You saw that in the benchmarks that Gregory provided. Code looks almost like what you might write on paper or pseudocode. And I showed you, both of us have showed you some examples of that. You can see that it is very easy to build, even like a neural net. What Gregory showed you is how you can build it from scratch, and that will run almost as fast as the more optimized libraries. But you have complete control over what the network looks like, and you can tweak the standard options. That's really the advantage of using a package like Flux, but of course you can use the standard packages if you want. This came up in the chat. You don't have to make unnecessary copies of the data, of large data, if you're using pass by reference. We find this enormously useful in our algorithms, because we can control the memory use, and things are much faster when you do that. Calling other languages is easy. Gregory gave you a bunch of examples. And you have greater control and transparency of algorithms, such as the neural net example that Gregory showed, because your prototype is going to be almost as fast as the compiled version. Has a very nice package manager that supports reproducible environments. So not only what package dependencies you have, but all the different versions of each of those packages. So it's very useful to reproduce when you are picking up a project like 2 years or 3 years later. And it has all the standard stuff like graphics, report generation, version control, debugger, and compatibility with many IDEs such as Jupyter. I think some people like RStudio. I think in the chat we found out, but there are to each their own. So what is our wish for the future? I think we would like to have an expanded and more complete ecosystem, even though you can call R and get the functionality that you want for the gaps that there are. You're still calling R, and your performance will going to be worse than calling R if you're calling another language. So it's better if those gaps are filled and the ecosystem is more vibrant. More learning resources, and this lecture is part of trying to build that. Language maturity, the language, when we started out from in 2015 to now, a lot of changes have happened and we have had to update our packages several times. I think now it has stabilized, and hopefully it'll be a lot better from now on. And finally, because there's this just-in-time compiler, it's sometimes useful to have static compilation for standalone binaries. That's there is something like that, but it could be better. So in summary, Julia is an attractive language for data science, easy to program with powerful abstractions that you can use to reuse and make it easy to read and maintain your code. It is an interpreted language with the speed of compiled languages and has a growing package system, which I hope some of you here will contribute to in the future. Some things that we have not covered is details about what multiple dispatches, just-in-time compilation, how you can tweak it, parallelization, multi-threading, using GPUs. These are important to some people. We can maybe talk about it in the discussion. Type system, meta programming, these are also things that more advanced users might want to talk about. So who should consider Julia? It's a great first programming language. If you don't know any programming, maybe you can consider this. If you are using R and want better performance, maybe you can consider Julia. If you have an abstract idea that you want to implement in code, and you want the abstraction to work in a variety of situations, like Bayesian inference, this is a good language to implement that. And tool builders wishing to test ideas quickly. That's our situation. We are building algorithms and we want our prototypes to be fast, almost good enough for production. So that's our reason for picking up Julia. Who should not consider Julia? If you're happy with your workflow, then fine. There's no need to change. If you are needing specialized packages or functions that are already existing in your R, Python, or whatever, and they are computationally intensive, then maybe you want to just stick to that. We're happy to answer any question, and here's a bunch of resources that you could look at, and we are going to post all of this on the OPAR website, so you can look at all the material, the notebooks, this notebook, and other resources and this video if you come back a few days later when all of that is posted. Thank you so much, and we will take questions.
Well, I have about 18 questions, but I will wait, and hopefully some other folks have questions before me.
Oh, okay. There is one question in the chat, which is, when will their resources be posted? They will be in a few days, certainly within a week, they will be posted. Where they will be at opar.io. And let me also put this in the chat. Okay, Gabriel, I think might as well start. I think you already had a question in the beginning, which we
let's start the suffering, I guess, shall we? Thank you. First of all, thank you for the presentation. I've been wanting to kind of dip my toes into Julia for a while. Back when I was in my PhD, I had some friends that were working. At Baylor, we had a lot of connections with Texas A&M, and there's a group at Texas A&M that does a lot of work in Julia. And so they were showing off some of their stuff, and I went to try to use it. And I think within about 2 months, the functions that I were using had changed so dramatically that my code didn't work anymore. So I said, okay, I'm going to hang up Julia for now, wait for it to get more stable, and then come back to it a little while later. And it sounds like from your presentation that that has happened. So I am very happy to pick up Julia again. I had the original question about the different kind of, there was one kind of slash that you used to divide to find the inverse of the X transpose X matrix. And then there was another function that was inverse. But I guess the more high level question would be, what is the process for developing code for Julia? Because I do like a lot of R package development, both for CRAN and for Bioconductor. And I'd be interested in seeing if there are a lot of meta language resources in Julia, such as, for instance, R's dev tools or that helped of new packages.
Yeah, so I think Gregory might have something to say, but let me start by saying, so first first about this. So this is a backslash operator. So this is for solving a system of linear equations, whereas this is taking an inverse. So, so they are similar, but slightly different. Usually the solving a system of equations for this type of, here it is going to be slightly faster because you avoid calculating the inverse. But in other situations, you have to calculate the inverse. So like this. Okay, what is the process of developing like? Now, this is where I think people have different opinions and workflows. Now, I'm a little bit old-fashioned. I work in Emacs, okay, and I can do everything in Emacs. So my work, the way I work in R is the same as in Julia. There's no change. But I understand that not everybody is like that. I also use Jupyter both for R and Julia, and they work pretty much the same way. A lot of people use Visual Studio. I think in our group, at least one person used Visual Studio. We used Atom for a little bit, but I think now the momentum in Julia has shifted to Visual Studio, which I'm told is fairly good, but I don't personally use it on a regular basis. Gregory, you want to add something there?
Yeah, so I actually, first of all, we will, in the resources that we'll post on the website, there will be links that will show you like some tutorial workshop or to how to do it, basically like I will share my screen. So this is an example of how it will work in Visual Studio. I'm working on the packages matrix LM2, which is like a model that we have, and I implemented like elastic net penalization. But basically, like I showed you earlier, when you create like this generate, and you give the name of the module or the name of the project or the package, and it will create this infrastructure. So you will have the source directory, a test, and you have like those log file which will help like form the environment. And meaning like, for example, let's say that you write a project or you write a code, but you don't do like what I have done. Effectively, like if there is a new update of the whatever packages and you come back, you might have like some you need to change some of the code or whatever, you have deprecation, right? So but when you do that and you add those packages will stay there, and you can still have access to all of them, even if you go back like many years after that. when you load that, you will have exactly of what you have done. And also, basically, they are the dependencies of your project or your packages. So then after that, when you have your package ready, you have your test, your documentation, you have a process. This will be also sharing in the resources where you go. You basically has to be on GitHub. And then after, there is a website for registering the package, and you loaded that, and it will make some testing to see if it works with on Linux, on different kind of OS, and if everything goes well, so then after a few days after, or one day after, it will be officially registered. So.
And you could you use Travis CI or some other continuous integration? Okay.
Yes.
Okay.
Yeah. It's a requirement to register the package that it clear some sort of continuous integration system.
All right, that's fantastic. Thank you so very much for that. I'm going to need to start playing with some Julia now. One last question. What kind of keyboard do I need to get the fancy Greek symbols like the del operator and the alpha and the beta and all of that?
None.
Let me show you. Yeah, nothing here. So this is the right. So beta, like tab, like this, and then press tab. And so, so gamma.
That is fantastic. That's really slick.
Yeah. /pi, very convenient. Yeah, I forgot. That was something I was supposed to do. I forgot to do that.
So yeah, you see, so this is on the Julia documentation. So that is the tab completion for whatever characters, and so basically the list is very long. You see, so that's all the mathematicals like icon, or even like you have, I think it's at the end. Yeah, you have even emojis or this kind of thing. Basically, whatever it is, like in your Unicode, you will have the equivalent to do it, and you can combine them. Like for example, you can make a hat on a letter, or and so on.
All right, last question. Is there so if I am stuck in R, there is a very vibrant Twitter community, either for R for data science or for R stats, and I can usually shoot out a message or find something on Stack Exchange, Stack Overflow, but Twitter's a really great resource. If I'm stuck in Julia, where's the first place to go? And please don't say read the manual. Yes, I'll read the manual, but where can I get help?
Of course, is the best place. That's where the big shots hang out, and so that is for easy questions. I would just use Stack Exchange. I think that is fairly good. But if you're getting into like really kind of tough issues, Discourse is where the developers and like the package leaders of different packages and projects, that's where they hang out.
Okay, I think I've interrogated you enough. Again, thank you so very, very much for your presentation.
Thanks for your questions, and feel free to shoot us more questions. We are glad to answer.
I may take you up on that.
Okay, absolutely. Okay, have we answered the string manipulation questions, Shusheng?
Yeah, I told that basically you have like more or less the same functionality that in R with string R. You can use also the regex, function. So actually, it is. I've done both, and so of course it's a matter of it's subjective, but I like better Julia for doing like those manipulation. Because you have like this broadcasting functionality, which is very useful. So yeah.
So, and there was also a question or comment from Rupert overall regarding memory. Do you think it has been answered, Rupert, or you want to ask a question?
I think my question was answered there. It was just I was intrigued about the non-copying behavior of the. I mean, I'm an R user, so that's a bit unusual, and I've had some issues recently with parallelization and R sort of losing track of, you know, when you're forking the environment. That would be quite an interesting ability to be able to actually retain connections back to the original environment when you're creating parallel.
Mm-hmm.
Yeah. Yes. Julia, you know, there is a very nice kind of page on parallelization in Julia. So you know you can have all kinds of different ways of computing. There's multi-threading, there is distributed computing, there's parallel computing, GPU computing. All these forms of parallelization are possible, and you have great control over all of those. So, for example, there is a construct called shared arrays in Julia, which allows multiple processes to access the same array. So that does exactly what you're asking for, and we use it for some of our computations. You know, of course, there's a cost to all of those, but it is very convenient and it works very nicely. Similarly, you can do GPU computing, and you don't have complete control like you might have in directly in C++, but fairly close for a lot of things, like you can define your own kernel functions for the GPU in Julia, which would take a much longer, much bigger code if you were to do it in C++. And there's an example of that in one of our recent papers, which I can share in a little bit. Let me share the link. I put the link in the chat.
Yeah, while I'm on, I might actually ask another question. So I'm working on a package at the moment in R that's hitting some performance limitation issues, and it sounds like Julia might be an interesting solution there. But at this stage, I would want to retain the actual package in R because it's resting on a lot of existing code. Do you have experience using sort of embedding Julia in R, and should that be compiled, or is it, what's the best way to do that?
So one way to do it is to call Julia from R. You can do that. The other way to do it is to do what Gregory showed you earlier, which is you call R from Julia. So it depends on like how complicated the data structures and the computing is that what kind of infrastructure do you need from R is the question.
Yeah, so at this stage, I've got the package and all the handling and everything is in R. So I'd rather be going along the lines of calling Julia from R at this stage.
Right. But what is the
so the user will be installing an R package.
Right. So you can call Julia from R. But what you said, you are running into performance issues. But what is the block? You know, as far as you know.
It's a rather complicated data structure. Is all this time series behavioral data that I'm working with. So I need to run it in parallel, but it doesn't logically parallelize very well. So I'm sort of splitting up into big blocks and passing rather large objects, or in fact, actually complex environments to each in a forking cluster, and it's getting a bit messy. And you know, if you actually try and pass these objects, they're massive objects that take forever, and then you end up with that being the bottleneck rather than the actual computation, and so on. So this is where the question about shared memory came from. I've not had a lot of success using the shared memory constructs in R.
Right. Yes. Yeah. I think that. Yeah. It's probably yes. I think that we probably need to think hard about how you can organize, and if there is a way to use Julia if that would help you manage this issue. Gregory, you wanted to add something, I think.
Yeah, I think that like in Julia, in terms of parallelization, which is like multi-threading, multi-processing, you have like more, I would say you have, compared to R, you have more flexibility, and I think it works pretty well. I mean, so depending exactly of what is your problem, you might tackle like or go for the multi-threading or the multi-processing. And yeah, so I think if it is like one block in your program in R, like in your package or in R, yeah, definitely I will try to call Julia. Basically, it's like, let's say that if you want to do it with C, it is better to do it with Julia, in the sense that it will be easier to code it and to debug it with Julia than C. If you have someone to code it for you, I will use C. In this way, yes. So, but like if everything else is, you can do it in Julia, but just for this code to get like some data or whatever, you need to use your package. I will use like use it like R code from Julia. But I guess like from what you have said, I think it is you are in R and you need like, I think there is a package called Julia call, and you need like to do it. So I mean, basically what you need to do is like yeah, it's like when you export your object to Julia and try to code in Julia to first like to be sure that object like structure in Julia, and then after there is a lot of tutorial, a lot of good workshop. There is actually a very good workshop. I'm following it now. It's called Julia Academy, or right, Saunak? You put it in one of the resources. And there is a free workshop you can follow, and they give you like more in details, like what are the different aspects of the parallel processing in Julia, and more also detail, and there is some exercise. So I will try to invite you first, like to go and check this if it might like fit your problem first.
And Rupert, we are happy to talk more if it is helpful. Just, you know, if you want to sound out.
I'll certainly have a go with Julia, and I've not used it before. I'll check it out and get back to you with some more informed questions.
Sure.
Spencer, did you have some questions?
No, I was just curious about whether the performance was affected moving back and forth between languages, but
Yes,
unlike
there would be a cost. Yes, there is a cost. Yes. So I think for that reason, you don't want to, you have to be careful about that. Like if you're moving, passing a large data structure back and forth, then yes, it would be better if you passed it once into Julia and then kept it there.
right.
Whatever, you have to manage it that way.
Yeah.
Yeah. So definitely that for that reason, just calling other languages is reasonable, but is not ideal.
Right. Thanks.
You're welcome.
I think we have hit the 1:30 mark. If any of you have any questions, this is the last call for questions. And if not, thank you all for listening. We'll post the notebooks and resources, and both of us remain available to answer any questions if you have. And we are happy to chat or, email, whatever, thank you all.
Thank you all.